Now, looking at example 2, we haven't done anything yet to this problem. We haven't put it in an augmented matrix, but how do we know that we're going to have infinitely many solutions or no solution just from looking at it? Less equations than variables. So we don't have enough equations. So we don't have enough equations to solve for an x, y, z coordinate. So how many equations do we have? 2. How many variables do we have? 3. So less equations than variables, we know we are going to have a special case. So since we're going to use reduced row echelon form here, we don't have to worry about simplifying the equations first or trying to get a 1 in that top left position because our calculator is going to do all the heavy lifting for us. So we do still have to show our augmented matrix. So 2 and 3, 3 and 5, negative 1, positive 1, 1 and 3. So to do RREF on our calculator, where do we go to access the matrix? Perfect. Second x to the negative 1. To type in the matrix, we're going to go to edit. Now this one is different because what are the dimensions of this matrix? 2 by 4, 2 rows, 4 columns. So 2 by 4. Let's type in that stuff. After we have entered in the matrix, what must we do next? We got to go to second mode to quit. So you have to go to the home screen before you can do that matrix operation. So then you go back to the matrix, second matrix, to the math button, and then all the way down to reduce row echelon form. Then back to the matrix, second x to the negative 1, and select that matrix A. And if you're like, if we already know it's going to be IMS, like why are we even concerned with getting that reduced row echelon form matrix? This is going to make our numbers a little bit smaller. We've got our zeros in those positions that we need. That way we can actually get legit expressions for x and y. So our reduced row echelon form matrix, 1 and 0 and 0 and 1, negative 8, 5, and negative 4, 3. So again, folks, it's important to note this second scenario where we can get IMS, because if you're looking at this going, there's no 0 equals 0, why is this IMS? Well, if you look at the columns, I've got the 1 for the x, I've got a 1 for the y, but then there's no equation to give me the 1 for z. So this is how I know that z is going to be my reference variable because there's no third row. So z is the ref variable again. So we want to come up with an expression for x and y only in terms of z. So let's go ahead and transform that second row back into an equation. This says 0x, 1y, or just y, plus 5z equals 3. How do I solve for this expression for y in terms of z? We're going to minus that 5z. So y equals negative 5z plus 3. And again, I like to put my variable stuff first before my constants, but it doesn't actually matter. And now I have an expression for y in terms of z, the reference variable. Now we're going to go ahead and do the same thing for x. So moving up my matrix to the next row, turning this back into an equation, we'll have x plus 0y. So that's the nice thing about doing this in reduced row echelon forms. I don't have to mess around with that other variable. And then minus 8z equals negative 4. We add the 8z, and x is equal to positive 8z minus 4. So we have an expression for x in terms of our reference variable z. So see if you can write that coordinate solution formula. Oh, perfect. So is it down in the main office then? Okay, perfect. I'll try to come down during 4th. Thank you. Bye-bye. All right, folks, so to write our coordinate solution, it goes in that x, y, z order. So our expression for x in terms of z is 8z minus 4. So when you're typing this in on MyMathLab, don't put the x equals because it's the position in the coordinate that tells you that that's what my x is. Then my y stuff, negative 5z plus 3. And then what do we put for z? Just z. And that is my coordinate solution in terms of z. Now, if we wanted to check ourselves, what we can do is generate a solution by arbitrarily choosing some z value. So I'm just going to choose my favorite value, which is 2. So what happens if I plug 2 in for z? Then y will be negative 5 times 2 plus 3. X will be 8 times 2 minus 4. And when I simplify this, that gives me 12 and negative 7 and 2. And what's nice about being able to generate a solution is I can take that and plug it back into both equations to check. So generate a solution and plug it into all 3 equations. So 2 times 12 is 24. 24 minus 21 is 3, and 3 minus 2, boom, it's 1. It works in the first equation. 36 minus 35 is 1, plus 2 is 3. It works in the second equation, so we can be sure that our coordinate solution, this guy, is a good way to describe any and all solutions to that system. And folks, you don't have to write that x and y below. That's just to show you that those are what those x and y variables are represented by. How are we doing with this, folks? Yes?
So when you plugged in the 2, is that just like a random number you picked?
Yep, I just arbitrarily picked something that was easy to plug in, something that was easy to generate. I'm glad you asked that because, folks, something I wouldn't plug in here is 0. Because let's say that you goofed and had this as a positive 5 instead of a negative 5. If you plug in 0, that's going to just wipe out those coefficient terms completely, and you're not as likely to find those little errors that you make. So keep it small, keep it easy, but probably not 0. Other questions? That was a good one. That's pretty good. All right, so we're going to go ahead and skedaddle on past this stuff. No number 3, no example 4, no example 5. And this is where we get into, well, what I consider the fun part, or the applications of why do we care about these infinitely many solutions, and why is it good to be able to have a way of describing the possible solutions. So folks, we're going to go ahead and go to page 10. And we're going to start by reading through this problem. There are 101 toys given out to a group of children. Games, dolls, and toy cars. A game costs $4, a doll costs $3, and a toy car costs $2. A total of $299 was spent. Find the number of each type of toy given out and how many combinations are possible. We're actually going to not answer that last question. That's something we'll get into on the next page, but we are going to start by trying to write an equation that represents this system. So thinking about totals we have. There are a total of 101 toys given out to a group of children. We can let X be games, Y be dolls, and Z be toy cars. So 101 toys total. What do we have representing the toys? X plus Y plus Z equals 101. So our unit is the toys. Then we've got expressions for money of how much each of those items costs. So $4 per game for X, $3 per every doll, 3Y, and toy car, $2. So 2Z. And this is equal to the amount of money spent, $299. And that's it. We've used all the information in the problem, so those are the only equations that we can write. So how do we know this is going to be IMS? We have 3 variables, but only 2 equations. So there's not enough equations to describe this to get a full-on solution. So this is how I know that there will be IMS. So not enough equations. To find X, Y, and Z. Now, normally, we would say that this is infinitely many solutions. Not enough equations, there's going to be an infinite amount of points on this line. We could here, and here, and here, and here, and here, and here. But if we think about what X, Y, and Z are representing, are we going to have 2.3 toy cars? Or negative 8.7 dolls? So instead of having infinitely many solutions, as we start getting into some of these applications, we're going to find that there's really just many solutions. We're limited here because we shouldn't have any negatives. So no negative stuff or decimal answers either. So no negatives or decimals possible for answer. So we're not going to have an infinite amount. There could be a lot of different solutions, but we're not going to have all of those itty bitty points in between all of those points on that line or on that plane. So if I asked you to solve this, which would you prefer to do? Row operations, doing row echelon form, or reduce row echelon form on your calculator? Yeah, calculator please. So given the option on these story problems, we are purely going to use reduced row echelon form using our calculator. Now we still have to show the augmented matrix. This is considered appropriate work on the test. So 1 and 4, and 1 and 3, and 1 and 2, and 101, 299. And luckily for us, the dimensions of this matrix are actually the same as the problem we just did. So second x to the negative 1, edit. Our dimensions are still 2 by 4, so you can go ahead and type in those elements. Second mode, to quit. Now the nice thing is if you have recently done a reduced row echelon form problem, you can do second enter, which copy paste. ACT folks, that's a good strategy for you. Second enter is a quick way to copy paste the previous line on your calculator, save you a little time. And this shows me 1, 0, negative 1, negative 4. So then 0, 1, 2, 105. And that is my row echelon form matrix, reduced row echelon form matrix. So then what's going to be our reference variable? Z, because I have an X with that one, I have a Y with that one, but there's no third row to describe Z, so Z is going to again be our reference variable. So Z as the ref variable, because there's no row for it, and we're here for it, no row for it. I want you to see if you can take it from here. Find an expression for both y and z in terms, or sorry, both y and x in terms of that reference variable z. Check yourself. So we've got z minus 4 in our x slot, negative 2z plus 105 in the y slot, and z in the z slot. Folks, what questions do you have? All right, let's go ahead and turn to the next page. And check it out. This is our last problem of Unit 4. Woo! All right, so a restaurant owner receives a package of silverware containing knives, forks, and spoons. The box arrives with 40 utensils and weighs 141.3 ounces. A knife weighs that many ounces, fork, spoon. How many solutions are there for knives, forks, and spoons inside the box? So on this problem, we're going to take it all the way and find out how many actual solutions we will have for this problem. So folks, I want you to start by seeing if you can write the two equations for this system. Go. Don't forget that for writing these equations, it's a good idea to think of totals that you have and the units of those totals. So our first total is we have 40 utensils. What do we have representing utensils? Our x, our y, and our z. Then we've got a total of ounces. What do we have representing ounces? We have a weight for each of the different utensils. So 3.9x, 3.6y. You don't have to have that 0.0 with the z. I just threw it in to show that's where that was coming from. And folks, at this point, we have used all of the information in the problem. So how do I know that this is going to be IMS? Not enough equations. So not enough equations to find an XYZ coordinate. So if we have 2 unknowns, we need 2 equations. If we have 3 unknowns, we need 3 equations. So not enough equations here, but it's not going to be IMS because as we stated in the last problem, we have limitations based on the real world context of this. Our variables must be integers. That means no decimals or fractions. We also need our variables to be non-negative. And how we can state that is they must be greater than or equal to 0. Because that wouldn't make sense. We can't have negative knives and forks. So not enough equations to find x, y, and z. Our variables must be integers, and the variables must be greater than or equal to 0. So instead of having infinitely many solutions, we're just going to have many solutions. And on this problem, we're going to find out exactly how many solutions we can find. So folks, let's go ahead and write our happy augmented matrix. So 1, 1, 1, 40, easy enough. 3.9, 3.6. You can write 3.0 or just 3, and 141.3. Are we doing okay with using our calculator to do the reduced row echelon form? Okay, I'm going to save us some time, and I'm just going to tell you what that matrix looks like then. So we can get to the fun part of this problem. So 1, 0, 0, 1, negative 2, 3, 9, 49. So who's going to be our reference variable in this one? Z again, because there's no row for it. Here's my X column. Here's my Y column where I've got my ones. Nothing for Z. So Z is going to be my reference variable. So we want to get expressions for X and Y in terms of Z. So turning that second row back into an equation, Y plus 3Z equals 49. Subtract the 3Z. We get Y equals negative 3Z plus 49. Next row up, X minus 2Z equals negative 9, since there's nothing for the Y there. Add the 2Z. And X equals 2Z minus 9. So those are my expressions for X and Y in terms of Z. So my coordinate solution will be 2Z minus 9 for the X, negative 3Z plus 49, and Z. So X, Y, and Z. Now, this describes all the possible XYZs that will satisfy that 3-variable 2-system of equations. Now, what we are going to do is try to put these specifications in that say, hey, our variables need to be integers, and our variables need to be greater than or equal to 0. So we're actually going to start with the greater than or equal to 0 part of this. First, my X variable, 2Z minus 9. This value needs to be greater than or equal to 0. My Y value, whatever I get for that coordinate, that needs to be greater than or equal to 0 too. And then Z, yep, that too has to be greater than or equal to 0. So these 3 specifications are how we say no negative answers. So if I choose a Z value for my spoons, like 4, and it leads to a negative amount of knives, that's not a viable solution for my system. So we're going to figure out how we need to restrict our reference variable so that we stay within the positives for all of my other variables. Yeah? Let's go ahead and solve for this first one. We've got 2Z minus 9 greater than or equal to 0. So inequality time, folks, isolate your variable just like you would an equation by adding 9 over to the other side. So 2Z is greater than or equal to 9. Divide by 2. So Z needs to be greater than or equal to 4.5. But since we also have this specification that Z needs to be an integer, so needs integer, what integer is greater than or equal to 4.5? 5. So we don't round up for rounding rules. We round up because 4.5 is my minimum for keeping things positive. So we need to go above 4.5. So we're going to round up. So z greater than or equal to 5. So we've got a restriction on our z value. We move on to our next inequality because we don't just want the knives to be positive, we need the forks to be positive too. So negative 3z plus 49 greater than or equal to 0. Negative 3z greater than or equal to negative 49. We divide by negative 3 and, oh, folks, what happens if we divide both sides by a negative? The sign flips, boo, on top of all this other crazy stuff we're doing. So z would be less than or equal to, oh, it's about 16.3-ish. Now, here's what's tough, folks. For this, we also need an integer. So 16.3, that's no good. We want a z value that's less than or equal to 16.3, which would be 16. We round it down. So our expression will be z less than or equal to 16. And then I've got z needs to be greater than or equal to 0. Now, that may be true, but since this one says z needs to be greater than or equal to 5, which one overrides the other one? This one, because this says, hey, if you go less than 5 over here, you're going to get negative knives. So even though z is greater than or equal to 0 is okay for the spoons, this restriction overrides that one. So now we know that the number of spoons, which is our z, so z spoons can be equal to between 5 and 16. So this isn't an infinite amount of combinations. There's still a lot of them, but we, with these restrictions, can limit it to a few. So since z, my spoons, can be equal to 5 through 16, if I had an x, y, z coordinate, the z reference variables that we could use to generate solutions, we could have 5 for z, 6 for z, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And then I could find the corresponding amount of knives and forks, or x's and y's, that go with our possibilities for z. So each z corresponds to a specific x and y. So there are how many actual solutions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 actual solutions. So many, but not infinitely many. And that concludes Unit 4. we are gonna take a breather before we go into the homework packet, and we're gonna do another one of these story problems together, and then we're gonna throw back and start doing some more just row-out practice and reach row echelon practice. So folks, let's take a quick breather before we move on to the next